would have been specified implicitly, implicit as a function of time. And in fact, that specification implicitly would have been given by the statement of how the flows depend on the stocks. We'll be seeing that future times. Or if you have an agent-based model, it doesn't say explicitly what that model will do. The number of people over time will be infected. What it says is this person's, for this person to go from a susceptible state to an infected state, they have to receive a message. And if this person is in an infected state, they send messages to others and indicating that they're exposed to infection with a certain rate. That doesn't explicitly say how many people are infected. Those are emergent properties. It's emergent property of different equation, emergent property of that model. What a simulation model has, ladies and gentlemen, a dynamic model, is a state that evolves over time. At any one point in time, there's a state of things. And we could summarize that state using any number of different output variables typically. And maybe we'll have some behavior like that. That's in no way specified to the model. That's an emergent property. But at any one point in time, there's some state of the model. If I had a stock and flow model, it'd be stocks, which gives the number of susceptible, number infected, number recovered. We have flows between them, the number of people per day that are getting infected. Or maybe it's, cars, houses that are planned, houses that are under construction, houses that are finished. And there's flows between them associated with starting construction, finishing construction. What would the state of that model be given by? Current state being sort of the current status, a complete specification of the status of the model. What would it be given by? Stocks, flows? Actually by the stock. The number of people in each of those categories, the number of houses in each of those categories. That turns out that totally specifies it. In an agent-based model, the stock, the state is much larger in terms of specification than that. It really has to do with the state each agent is in, which is perhaps given by things like for each state chart associated with it, the current state they're in with respect to that state chart, the values of any variables associated with that agent. Maybe there's a variable for, associated with their current weight or their current income or whatever. That would be part of it. It's a much larger set of information that's the state. But at any one time, there's a state, and typically the evolution of that model, the behavior of that model, is specified as a function. So how the model will change in the next little bit of time, whether there'll be a transition or not. The rate of flow from one stock to another, that's specified as a function of the current state. So you specify sort of the delta in states as a function of the current state. And over time, the state evolves according to that. But you in no way specifies how that state evolves up front. And typically that's not possible to do. It turns out mathematically, for reasons that we'll probably take a peek at later in the semester, for most such models, it's just not possible to create a closed form description of this behavior. What do I mean by closed form? Has anyone heard that term before, maybe over in math? What does that mean? That I can't write down a closed form expression for this behavior over time of a dynamic model. What would that mean? Well, it means I can't write down a mathematical expression using sort of classic simple known functions. By convention, those include not only algebraic expressions involving polynomials and so on, but also traditionally involve things like transcendental functions, sine, cosine, and stuff like that. I can't write down, for a general model, I'm not going to be able to write down some expression that gives this in terms of those functions. It's just not possible. We can't anticipate what this is. It's a little bit like, for those from computer science background, it's a little bit like the issue of universality. of a computation that you can't anticipate ahead of time whether it's going to halt or not. The only way to find out whether it's going to halt or not is to run it long enough, which maybe you have to run it forever. You're never going to know if it just a little bit more it's going to halt. So it is with a function like this. We're not going to be able to write it down. We have to simulate it. Yeah.
It would be okay then to say that a dynamic model is not non-dynamic models are deterministic in their representation of the way, or is that false because at the root of the model is still pseudo-random generation?
Okay, so that's a good question. So the question that was raised had to do with your name? David, right. The issue had to do with determinism. Is there kind of a neat mapping of the issue of whether it's a deterministic model on the one hand to whether it's a dynamic model? That's a separate issue, it turns out, okay? So we can have dynamic models that are stochastic or that are deterministic. And in fact, most of the system dynamics models that we'll begin looking at in future lectures will in fact be deterministic, okay? So they do actually have a very well-defined, precise trajectory over time. It's just that we can't anticipate it up front. Our mathematics is not adequate. It's not up to the task of being able to figure out ahead of time what the expression would be, the mathematical description in closed form of the curve. And I would actually, although I can't prove this, I would conjecture that it's impossible for any civilization to have a series of mathematics which could create a closed form expression for any nonlinear system. For all nonlinear systems, they could write down a closed form expression. No matter how ingenious they are, you're never going to be able to do that. It's a pigeonhole principle sort of thing. You can describe some of them with it, but some are just not going to be amenable because there's only so many things we can describe with expressions. But more to the point, we don't know a way with nonlinear functions for most nonlinear systems like that, nonlinear differential equations or agent-based models. We don't know a way to solve it ahead of time. We can't go and create an expression like this. Now, there are some systems which we can solve like that, simple differential equations. How many people in here have taken a differential equations course? Okay, great. So you folks will have spent a fair bit of time using various techniques to solve differential equations. And there's a set of them that you can solve quite nicely. So you can do transformation of variables, and you can guess as to what the solution is and solve for the appropriate components for certain types of differential equations like linear time invariant systems, systems with capacitors and inductors and resistors. If you're an EE person, you can actually solve it in terms of exponentials quite readily. You can plug in and say, I'm going to assume it's an exponential that goes in. What's the exponential that comes out? And then any input you have, you just decompose in terms of exponentials. You know what it does for each of them. You know what its transfer function is associated with it, how it amplifies certain exponentials, damps others, or what have you, and out you can get your answer for how it will behave. Well, and for a nonlinear system, we can't do that. And guess what? Some people say talk about nonlinear systems is like talking about non-elephants. It's a very special sort of system that's linear, and that's true. But if you take nonlinear systems in general, you can approximate them by linear systems for short periods of time. So it's actually a very useful thing to talk about linear systems. But in general, we're dealing with nonlinearity, and we'll talk about what that means later in the class. But for a nonlinear system, we can't solve it explicitly. We can't write down this sort of function. And so while with traditional statistics, we have ways of matching up closed form expressions with data, solving the best fit or what have you. We can't do that with nonlinear systems typically. We can't do it with the sort of models we've seen already. Instead, we have to simulate those models and try to match them by adjusting parameters, etc. So dynamic models involve evolution of state over time, okay? Typically in a way that cannot be solved up front, okay? There are linear models around that you can solve, but in general, we can't solve them. And so we have to simulate them for those sort of models. We can't do anything but simulate them. we treat them as a computation, and we run that computation, which involves numerically integrating it. Numerically integrating, say, a set of differential equations, or running a discrete event scheduler to run an agent-based model and continuous time, or discrete event models. So dynamic models have evolving state over time. So we talked some about that, and it turns out that all three of these types of models we'll be looking at involve dynamic models, these models with evolving state, okay? So let's talk about this modeling process. What's sort of the process of modeling? And you'll see here several components to this, okay? It starts with problem conceptualization. It's a busy slide, I'll post it, and there'll be recordings of this, but we start with problem conceptualization. We go on to qualitative problem mapping, where we map the problem out in a sort of quantitative or qualitative or semi-quantitative way. Let's see what I mean by those terms in things like causal loop diagrams. We then go through a stage. So this has kind of given us a sense of what, at a high level, this is kind of like the high-level architecture, or high-level design of a software project. You're not saying all the details yet, but you might draw out a class diagram, for example. Or you might draw out state charts. Or you might draw out interaction diagrams or sequence diagrams. It sort of helps communicate, and helps capture high-level understanding of how it should behave. But it's not fully quantitative yet. You can't run it. I've had people before tell me, oh, you have one of these. Can't you just run it? The causal diagram. Just run it. Can't you do that? No, you can't. It's not precise enough. It'd be like taking some pseudocode, which kind of specifies the general elements of what you're trying to achieve, and taking some class diagrams and say, simulate this. Well, it's not enough to do that precisely. I could interpret it this way, that way, it's a hard thing to do. So qualitative problem mapping, we're not yet in the quantitative domain. But the intriguing thing, ladies and gentlemen, is that at this stage, we actually can get quantitative insights. That's the interesting thing. From these diagrams, we can get some understanding for what the dynamics likely is. It's not foolproof. It gives a large bounds of error, but we actually can get some insights. And more to the point, we can get insights not only quantitatively about the system, we can get insights about sort of how things work out there, what sort of key points that might need to be changed if we want to adjust system behavior. We get a lot of insight out of this. The next stage is model formulation. And here we're going through the hard work of filling in the details. We're saying, okay, look, let's make this very precise, this qualitative mapping. Let's specify for a particular situation what we're going to assume. And depending on the purpose of the model, something that back here, model conceptualization, we'll come back to in a big way. Depending on the purpose of the model, we maybe find acceptable doing model formulation that's rough and ready. Maybe our goal is to sort of see the different ways that a process depicted in this way can behave. We're not interested in modeling an exact company or an exact health system or an exact, computer system. We're instead just trying to get insight into sort of for systems which have structure like this, where things work this way, what sort of behavior is possible. In which case, a rough and ready model is often perfectly adequate to the task. On the other hand, we may want to build a model that gives us quantitative trade-offs between this policy or that policy for my ordering or what have you. In which case, we want to build a model that's pretty tight, pretty careful. Just like a flight simulator, you might give out a flight simulator to people, which is, it's pretty loosey-goosey in terms of its depiction. It's not supposed to be for an exact plane as manufactured by an exact manufacturer. And people can have a lot of fun with that. They can get sort of a feel for how the planes behave in terms of the throttle and in terms of rolling, etc. But if you really want to train pilots who are going to be flying Concorde, or they're going to be flying, the 787, and that's going to be their focus, you want to give them, or you want to be flying, flying a stealth fighter or something. You want to give them that particular plane in the form of a simulator, and it should be really adapted to that plane so that they develop very precise intuition for that plane. And so it is with model formulation in general. Sometimes you really do the due diligence, sometimes your needs are more so you can be kind of rough and ready about it. Model calibration, for those models that you really care about the details, you'll then match it to data. So in general, we can't do the sort of linear regression, or for that matter, logistical regression or exponential regression. We don't have that luxury. If we have some data and we want the model to try to match it, we can't do a sort of regression type approach where we just say, okay, figure out what these parameters must be to match this. It can't do that without running the model. We can't figure out what the behavior is without running the model. So for a given combination of parameters, to figure out what its behavior is, we have to run the model. And we can then adjust the parameters so that it best accords with data. And typically a model like this will be very different from a statistical model in the sense that a simulation model will typically have many possible outputs. You know, a statistical model typically gives one thing. What do we call this? Like if t here, what do we call t and what do we call y in statistical terms? Can anyone tell me? This is called a what variable, and this is called a what variable. This is called a independent variable, and this is called a dependent variable. And for a given statistical problem, it's typically one of those. With a simulation model, we may have lots and lots of variables in the model. What we call output and input is really kind of up to us. They're all often or many of them are often dependent variables. They're adjusting, you know, simultaneously. So in general, we're going to have many outputs from our model, and we may try to simultaneously match them against various sorts of data. Now, on this diagram, model calibration and model testing are put next to each other. The ordering is not particularly privileged. Often we'll do some measure of model testing before model calibration. And what this involves, model testing involves a couple of different things. So we might do sensitivity analysis of parameters, see how much certain assumptions matter for a model. We kind of talked about that a bit last time. Cross-validation is a best practice. So cross-validation would basically say, okay, look, you have all this data at your disposal. Take some of it and calibrate the model against it for sure. Adjust the model parameters so it matches it as best possible. But take some of that data and reserve it and see if the model can guess it, even though it hasn't been told about it. If the model is actually representing pretty well the way things are, it should be able to, in a good solid model, should be able to predict some things that you wouldn't have otherwise used to build it. It should be able to anticipate things going forward that you haven't yet observed. And so if you're counting on that, you should be able to count on it to at least fill in the blanks for what you know going back. Right? And so with cross-validation, typically we'll have calibrated this model, and then we'll say, okay, now here's the test. Predict these things that weren't used to build it in any way. And we could try to match up some things. Maybe it makes guesses about things. We'll go collect data, and other times we set that data aside. You deliberately set it aside, maybe a quarter of the data, and then you see, okay, is it filling in the blanks? There's a variety of robustness checks. Unit checking is a very important technique we'll be talking about in this class, where we go through and we check the homogeneity of units, for example, so that you don't do something silly in the model, like add a count of persons to a number of dollars, something like that. That can be done numerically. You add one person to $2, and you get out 3. It's meaningless. There is no meaning to that expression. The computer's glad to do it. 1 + 2 = 3, but it has, semantically, it's nonsense. And so we can actually do unit checking on our models to try to make sure we're not doing something silly like that. And at the first level, that's really easy. It's really straightforward to do that. We'll see how that can be done. And there's a variety of other tests, like extreme value tests. We see how well our model behaves in the case, certain extreme cases, like where there's no illness introduced, or where, you know, it's a hugely sort of hugely communicable illness or what have you. We see, okay, does it behave in a sensible way? Very different from statistical analysis, where this sort of equation might only be valid over small periods or something. We'll often be running the model over expected to behave under a wide variety of assumptions. Policy evaluation. Once you have a model you're confident about, you may use it to investigate trade-offs between policies. And then knowledge translation, use of it by non-technical people who may learn from the model. Now, all of this, so any questions about this? I'm going to go into this process in more detail in just a moment. Any question at a high level about this process? Yeah.
At what point do you might realize that your whole model is actually complicated? It seems like if it's complicated enough, you could do parameter sensitivity and fix the parameters in such a way that it would seem to describe the model.
Yeah, yeah. So, it's a good question. Your name? Ivan. So, Ivan's question is a very good one. So, you know, look, if we have a model with enough degrees of freedom would be the term used statistically, if we have enough moving parts, couldn't we be fooling ourselves? Like, we could account for anything. We could kind of patch it up to account for anything. Tweak this parameter, adjust that one. And this is one of the big reasons that cross-validation is used. To set aside this data, see if it predicts it. So we won't just sort of after the fact, you know, tweak the parameters to adjust for that. But the point remains that if you have a model that's complex enough, it is a pretty broad area over which, you know, it could operate. The practical experiences that, and we're going to see this in a big way in this class, and I think Robin's at one, in fact, is going to have a little example of this sort. Turns out that if you have a certain model structure, so there's a saying, and it's particularly seen in system dynamics area, model structure determines behavior, okay? What I mean by that is, you might think, and this is a difference with statistical modeling too. So with statistical modeling, there's some other sort of notions like overfitting and so on, where you have a model that has enough parameters in it. You know, it has some various covariates like x, and then has interaction terms like x times t, and all those sort of things. You can get it to kind of match any data you want. And the more complicated this expression is, the more precisely you can match this sort of data. And there's a question of overfitting. To what degree are you just matching the vagaries of that data that you happen to get and coming up with parameter estimates that are not particularly general? And to what degree are you actually capturing something more fundamental that doesn't depend on the error associated with this data, et cetera, something that captures the underlying pattern. And there's a certain element of that in simulation modeling, but there's much more of a constraint in simulation modeling associated with the implicit specification we get. We'll see it in system dynamics and nature-based modeling. So only so many things that a model with the structure you see can do. So it only has so much flexibility. And you're not, of course, not programming that in. Here you're kind of programming in. With statistical model, you're kind of directly imposing the shape that you want to see. With simulation modeling, that behavior is emerging from there. And very, very often, I can't tell you the number of times as a practical simulation modeler, whether working in industry or in academia, where I have built a model that I think should be a pretty good model. I've taken it to data, and it just will not accommodate that. And whatever values of the parameters, there's just no way. Cannot do that. It cannot produce this pattern. It's not within its range of possibility. It's quite unlike the statistical model here, where with enough jiggling around, I can get it to match it. It's just again, structure determines behavior, and there's enough sort of specificity of that we just can't get it to match the specific of the data. So I have to go back and I have to adjust my assumptions of the model. And sometimes, not infrequently, I have to go collect more data to sort of say, okay, could this be going on? Now that process, I'd argue, is a very useful process, because that's how you learn about the world. You know, you say, okay, I think this is the way things work. That's my mental model right now. This is the information I have about the world. Do they jive? Do they match up? And the answer often is no, go figure. And then I go back and I say, okay, you know, what could be wrong? And you go talk with the relevant people, you go collect some more data, or what have you, and you come up with a better understanding of what may be going on. That drives your hypothesizing forward. Now, it is true that at some point, if your model gets rich enough, by sort of tweaking it, you might be able to get it to do this, get it to do that. And so it is with our mental models. And this is one of the reasons we try to keep our models somewhat simpler. There is ultimately a situation where, by appeal to special cases, you might be able to explain a wide variety of stuff. And that's where we use Occam's razor. You know, this idea that if there's two explanations, the simpler one is generally the preferred one, unless there's evidence otherwise. So I would say here that models are thinking tools. They're not going to tell us what the situation is. But the amazing thing is, from my experience, compared to statistical approaches, just how often they just kick back at us and say, can't be. No, this doesn't account for this. This doesn't jive. This is not consistent. It's on the face of it implausible as a hypothesis for how things work. Go back and refine your hypothesis. And that can be frustrating at the moment, but a very good thing for scientific exploration. Okay, so we'll see more of this, Yvonne. But fundamentally, it's a deep question, and I don't think simulation models are immune to it. But from my experience, they're quite a bit less adversely affected than statistical models. It's a lot easier to tweak up a statistical model and get it to fit whatever data you want. Okay. Great question. Other questions? Okay. So one thing I want to emphasize here, and it's associated with these kind of iterations up here, is incremental development. I mentioned this last time a little bit, and it's absolutely key. When we build a model, we typically try to do so incrementally. And there's several reasons for doing it. Some of them are classic software engineering reasons. So some people in here have taken software engineering classes before. Give me a reason from software engineering why I might want to build a program incrementally. Yeah. Yeah, early feedback from the stakeholder, right? From users. Make sure that my requirements, that as I understood them, are grounded in what they actually want. That's a great reason. How about another reason for software engineering? Why not just do the whole hog? You know, wait to get all the features in there before you build it and try to ship it. Good, good. So you might see early on, for example, if you start building and incrementally, you might see early on performance is a dog with a certain algorithm, or this becomes a real bottleneck. You know, it's this particular issue of performance. Bugs, though, are a key issue. If you build it up incrementally, you add one feature at a time, you often will see very quickly where your bug came from. Be able to, if there's something that goes wrong, you'll be able to say, oh, it's something I just did, so it can only be related to this issue. And you can quickly zero in on that. So that's an extremely important sort of motivation. It turns out there's several others. One is improve morale. I mean, it's nice to see things come together. Another is time boxing. So if you only have a certain amount of time, you don't know how far you're getting. You may have a good estimate. You may put down some estimates based on decomposition techniques we discussed in 371 or what have you, but you know, there are surprises. Maybe even despite the best risk management, you get bitten by things, this takes longer than anticipated, what have you, and you may not get as far as you want. If you build it incrementally, at least you got something. You got something along the way, right? You have something built up. There's some others too. Prioritization. You know, when you get feedback from the stakeholders, they might tell you this is off, or they might say, you know, what's really most important to me is this feature. That's what I'm really most interested in. And so it is actually with modeling. You know, so for the people who are experts about the system, I work with people like this all the time, and you know, they're familiar with the system for day-to-day work, and they'll say, you know, I think the main thing that's not incorporated at this point, the most important thing is this, or you know, that's a really puzzling result. I think we got to check that out because that's a very important topic for practical decision making. So clarity and prioritization, being able to change your sense of what order to add things in is a key benefit of doing this incrementally. So, and that's related to flexibility, change direction as important issues become clear. But importantly, folks, in the area of modeling very specifically is this issue. We're trying to learn from these models. They're thinking, they help us think more clearly. And if we put everything in at the, you know, we just wait to run it until everything's in, we see some behavior, we don't know where it came from. This is it's all added in together. It's all a jumbled mishmash of these things. You don't know what behavior is coming from what. If you add things in incrementally, you first add this phenomenon and that phenomenon, even if you think that they're all going to be important, you add them in incrementally, you see the behavior come from each of them. You say, oh, that's where, you know, for example, you add in that decay of immunity we saw in that first lecture. That's where the waves start to come in, you know, these sort of multiple waves. Or, you know, you start adding in some additional components with asymptomatic people and not asymptomatic people, and you get some other behavior where it sticks around or what have you. You basically start to see important patterns emerge, and you can connect them to particular things you did associated with the model, and it lends scientific sort of clarity about what thing is causing what. This is particularly important because, ladies and gentlemen, with modeling, it's actually really difficult sometimes to determine what's a bug and what's an emergent problem. You see this wild behavior. Wow, that's really neat. Now, is that just an artifact of your representation, sort of some approximation? Is it an actual defect? You did something silly, or is it just some surprising dynamic you just wouldn't have anticipated because it involves this complex nonlinear interaction you wouldn't have known? Getting a handle on that is sometimes very difficult, and if we can do it incrementally, especially if with each new version we create, we can disable the features we added and make sure it matches the behavior of the previous one. That's called docking, D-O-C-K-I-N-G. Docking behavior, so we add something in, we actually disable it, make sure, okay, it does the things we did before, so we haven't done something silly. Then we enable it and play with it a bit. That docking phenomenon can give a great deal of confidence you haven't done something silly, you haven't introduced a bug or what have you. So this whole process is done incrementally. And it's done incrementally as a whole. In fact, you kind of go through a fair bit of this at a time. It also can be done incrementally in terms of like going between model calibration and model formulation. So as I said, I can't tell you the number of times where I've had a model, I formulate, I try to calibrate it, just it's stubborn, won't behave in the way I anticipated at all. There's no way it's going to behave in this way, so I go back and I re-examine my model formulation. And often I end up going back and adding something into the model, documentation. Okay, in the interest of time, I think I'm going to skip fairly quickly through these components. So it turns out that this modeling process is sort of underdeveloped in modeling. An understanding of it, an appreciation of it. It's underdeveloped in modeling compared to software development. So I work in software development, I've worked as a professional software engineer. And there's a lot more theory there, a lot more methodology research than there is traditionally in modeling. System dynamics community has thought a fair bit about modeling, and some people are starting to do this with agent-based modeling. We're going to talk about this in a way that covers these different frameworks. For agent-based modeling, this is a framework, the party framework, properties, actions, rules, time, and environment for specifying a model. The idea here is give you some guidelines when you specify a model, when you describe the model. But often these help give thoughts for that early stage of model development, qualitative and then quantitative. So what are the properties involved, or the actions, the rules, time, and what's the time horizon, what's the time step, and what's the environment you're dealing with? Is it a spatial environment, dynamic environment? More geared towards specification. And there's a second framework called the ODD, the Overview, Design, Concepts, and Details Protocol. And this is starting to move more towards a sort of process for developing models. Its primary focus was specification, but it's increasingly being used as a way to sort of guide the successive development of these models. And it was a consensus protocol from a variety of agent-based modelers. So there's three components here: model goals and high-level scope, different aspects of design, and remaining elements. And I'm going to map them onto this framework here, okay, so that we kind of have an understanding of where they are. I guess I should have noted earlier, and this slide is a bit misplaced. When we're talking about the model framework here, typically it's conducted in an interdisciplinary team. Sometimes you're modeling something you know very well as a computer scientist. Operation computer of a network of distributed nodes, for example, of computers. That's very comfortable. But often you're dealing with things that are outside your scope. And even within computer science, you may be dealing with certain issues on the system side you're not an expert in. You need to bring other people in. It's an ongoing process of refinement, and I've noted the iteration. The observation here is that agent-based modeling, the focus, ladies and gentlemen, is typically on this. It's down on sort of this stage. It's been on quantitative insights from the model and the model itself. In system dynamics, particularly, there's an emphasis in the modeling process. The whole process is yielding insight. The whole process is giving value, both in terms of kind of intellectual understanding and in terms of bringing a team together. So there's a little bit of a sense of modeling as kind of as itself being an intervention, as achieving something. And that includes, for system dynamics, things early on like qualitative problem mapping, which is a stage that's traditionally somewhat a lot downplayed in nature-based modeling, which really goes for the quantitative formulation. Okay, so let's talk about ODD, this overview, design concepts, and details. So the first phase of ODD really is dealing with these problem conceptualization and problem mapping. And then design components and details is really dealing more with the formulation stage and going forward. We're going to talk about this. So I introduced last time this co-evolution where, models are thinking artifacts, we cast them into a form that's runnable, we make observations about them, and we have observations about the world, we make interventions to the world, we check their consistency. And if we have several models that might be applicable, as Yvonne indicated, what you might do is to undertake an intervention where you can measure something new, or you collect some new sort of data. Okay, let's talk about this. So the first thing I want to talk about is problem conceptualization. So those who are in 371 can use this term will know that when it comes to leverage or the impact of a mistake, the leverage of exerted by a bit of work. The leverage is actually much greater here. If you can avoid a mistake early on in a project, it can save a huge amount of time later compared to if you discover that mistake midway through. Okay. Problem conceptualization is arguably the most important component. The key point here, and this is one of the most important points of the class. You don't build models of a system per se. You build models related to a problem about that system or related to a research question about the system. And the issue here is that you're not going to be able to build a perfect model of the system. It's like trying to build a perfect map. What's the perfect map of Saskatoon? Perfect map. It is total detail in all elements. So I can use it to figure out where water flows. I can, when it rains, I can use it to figure out the electrical connectivity. I can use it to figure out where to drive. I can use it to figure out where to go walking. I can use it to figure out, where my dogs can run, whatever. Can we build a perfect map of the world? Why not? Well, that's part of it, yeah. So there's some limitations there. So if you really care about the curvature of the Earth, if your problem is such that that makes a difference, that's going to cause a problem there. But what's another reason, even if we could impose it on a little globe or something like that? What would be another problem trying to create a perfect map? Well, it might be pretty unwieldy. It might be pretty slow. You wouldn't want it on the dashboard of your car. You wouldn't want to carry it around in your pocket, as you're driving around as a pizza delivery man. The only perfect map of the world is, you can see where I'm going with this, is the world itself. And it's going to be just as messy as the world. And we're not going to get much insight on it. If we're trying to learn from a model, we have a model that's a perfect representation. It's going to really limit our insight. Okay, yes, we could do some experiments in there that would be unethical in the world, or would be impractical to do in the world. We might be able to do that, but the chances, probably be incredibly slow to run these experiments. We might die before we even run them. Just like the world. We'd have to wait, a generation to see how the next generation would play out or what have you. So, ladies and gentlemen, it's not going to be a perfect, just as there's no perfect map of Saskatoon or some area, it's not going to be a perfect model of the world. The models are going to be specific to purpose, just like with maps are specific to purpose. So when you want to figure out driving through Saskatoon, you get street map. When you want to figure out issues with hydrology, you get a topology map. When you want to figure out something about electrical connectivity because you're doing, power, high voltage power transmission across Saskatoon, you go for an electrical connectivity map. If you want to figure out why sewers are backing up, you look at a sewer-related map together with hydrology. So it's specific to purpose, and for a good reason. For good reason. Model purpose is absolutely central. Okay. So the quip that's often used here, George Box, there's a famous statistician, George Box, where the same issues apply in statistics, who commented that all models are wrong, some are useful. And you have to take it with a grain of salt. It's wrong in the same sense your map is wrong. So if you have a street map, is it wrong because it doesn't depict, the paths between streets and the pedestrian paths? Is it wrong because it doesn't depict where the sewers are? Is that wrong? Well, you can kind of argue with that. I mean, it's wrong in the sense that if you think that it represents reality, it's wrong. But if you're looking to it for a purpose, to guide you in terms of driving, no, it actually may not be wrong because of that omission. In fact, it may be more useful. You wouldn't want, imagine if your real map of Saskatoon, you have to, brush away the trees to see where the street went. That'd be a real pain, right? Or you have to peer out from the grass. What's going on over there? So all models are simplifications, and they're wrong. in that sense. They're wrong in the sense that they don't correspond perfectly to reality. But some of them are useful, and useful for a purpose. And one of the biggest problems that students have, even in some experienced models, is trying to create a perfect representation of a real-world system, particularly if you try to do it all at once, rather than incrementally. Incrementally, at least you learn along the way, even if you never get there. But try to keep on throwing things in. It can be disastrous. It can be disastrous in terms of deferring insights, preventing insights. So establishing a clear model purpose is critical. Explaining reference modes. What is your goal to explain some behavior you've seen? Maybe it's behavior over time. Maybe it's behavior over space. Maybe it's some pattern that you've noticed. Maybe you want to explain it. Maybe you want to understand, broad trends, what's driving them, and so on. Understand policy impact. What's the trade-off between these policies? Maybe you want to rule out a certain hypothesis. We're trying to see, could this hypothesis, taken in isolation, account for this odd behavior? Is there a very simple reason for this behavior? You want to think explicitly about model boundaries, and we'll get to that in a second. And adding in factors often does not yield greater insight. Sometimes it can obscure insight. So you got to be careful. Sometimes the simplest models give the greatest insight. And sometimes what we do is we build up a model that's fairly complex, and then we take out the pieces. We say, well, actually we can boil it down to the purposes of insight and to just these couple of things. We might not use that simple model to predict trade-off between policies, but we might use it to sort of communicate an underlying truth. It's like a caricature. So what's the caricature used for Brian Mulroney? Anyone remember? There's certain things that are exaggerated about his face. Yeah, it's his chin. So it'll have it sticking out. And you recognize it immediately. Okay. And it communicates some underlying truth. Okay. He has a distinctive trend. But it's not a perfect representation of things. And sometimes models are like that. We'll see some really interesting models in this class which are like that. They communicate something very deep. One model, for example, we'll look at, it's called the Schelling segregation model. And it's in any line, so you could go on if you wanted to. It's one of the example models. And basically it shows how the emergence of segregation, emergence of broad patterns of residential segregation, where you have, those modeled particularly in the States, where you have whites and blacks, big patterns where they sort of live in different neighborhoods. And it explains that by just very small differences in preference. You don't need everyone to be incredibly racist or something like that. They just have a small preference, maybe based somewhat on economics or based somewhat on kinship or friendship or the existing social networks, what have you. Turns out that can explain it. And it's showing something that might be unexpected otherwise, that you don't have to attribute, really, really nasty sort of sentiments to people. These things can emerge from very small patterns. So great people have commented on importance or purpose, and this cuts across system dynamics world, John Sturman, Railsback and Grimm, with agent-based modeling. So let's talk about this for agent-based models, where the issue is particularly key. It turns out that system dynamics modeling, we're more hemmed in by the nature of the framework in terms of what we can do. With agent-based models, we could just throw the kitchen sink in. And the point is there's a high opportunity cost. When I talk about an opportunity cost, what do I mean by that? Can anyone tell me what I mean by opportunity cost? So when I make a decision, what is that? Maybe that gives me some benefit for having made that decision, but what does it also do? Exactly. In fact, the very Latin term decide means to cut off a branch. I've gone this way, not that way. So opportunity cost is associated with the value of the opportunities foregone. I made this, I put this into the model. How could I have used that time instead? This is a question you should often be asking. Sure, maybe I got value from adding this in, but maybe I could have taken that time to run the existing model and gotten some insight into it. Or maybe I could have broadened the model instead of making it deeper. In other words, because I chose to do this, I didn't choose to do these other things, and I need to consider them if I'm going to do sort of a cost benefit. Given a limited time we have available, limited resource more generally, it takes away from richness elsewhere. So we got to be quite careful. When we add things into the model, we got to be careful to realize that this time could have been spent examining a broader set of intervention options, or it could have been building up a separate model that accounted for this other thing. We need to be quite aware of that. So the goal here is to use monopurpose as a sort of logical knife, as John Sturman comments, to cut away unnecessary complexity. And there's a principle from agile software development called the agony principle. How many people have heard of the agony before? Anyone? Okay. You ain't gonna need it. This is the agony principle. Now, what it's basically saying is start simple. Don't put things in speculative. You think it might be, so we'll throw it in. Do that incrementally. If you're going to need it, add it in at the right point. Just don't throw it in up front. Don't get into all sorts of speculation, because you will learn during the modeling process, and you may decide, okay, to put something else in instead. So don't presuppose things up front. In software development, this is about not putting features in that may not be needed. Don't just throw, they may do this, that. No, give time for it. Get stakeholder feedback. Their priorities may be elsewhere. Don't just gold plate this thing at the cost of foregoing, giving value to stakeholders early on. So this is arguably one of the most important slides in the course as well. This is something I will hold you accountable for. And chances are as good as not that'll be on our first pop quiz. And one of the things, when you approach a model, this is one of the questions you should be asking. A dynamic model is a bulk state. This gets to the heart of elements of dynamic modeling. There's three distinctions we want to make between things. When you're thinking about things in the world related to what you're trying to model, you're thinking about that spread of infection in a population. You're thinking about how companies form strategic partnerships, or how innovation spread, IT innovation spread across society. And you want to build a model of that. For each incremental phase of that model, you're going to want to make the distinction between three sorts of things. Some sorts of things, down here at the bottom, you're going to reflect on. That's an interesting phenomenon. Someday I'd love that model. But, I don't think that it's likely to be that important. Maybe it will turn out to be. My guesses are wrong, though. But for now, I'm going to leave it out of the model. Maybe I'll add it in a later stage. That's excluded from the model. It's ignored totally. We just don't have it in there. But we have made the conscious decision to avoid putting it out. And so we have it on our list. Oh yeah, we thought about that, but we decided to leave it out. Example. I'm on a long project run out of Columbia University looking at obesity in New York City. It's an Asian-based model, looking at that. And they decided there's all sorts of things about residential neighborhoods and some issues with people's mobility and how much they eat and sort of physical activity and stuff like that. And it's intergenerational, so there's kids that are born in the model that grow up and there's effects of childhood, etc. But they decided to leave out, this is particularly key for age-based models, because we're depicting things at such a level, we can put all sorts of things. They left out procreation, per se. They don't have people coming together in partnerships, males and females. In fact, they don't even distinguish between males and females. They don't have males and females joining up, having kids together, have a father and mother. In fact, people just bud in the model. There's a baby born near the parent, and it abstracts over whether it's mother or father. It just gives rise to, and you might say, well, that's bullcrap. I mean, that's nothing realistic. But that's not the point. It's like your map of Saskatoon leaving out the trees. Okay, yes, you could go model, You could go model the marriage market. You could model, single motherhood. You could model, relationship formation and dissolution and risk of pregnancy. But that's not the point of the model. You could spend years doing that probably and create very interesting models. But there's an opportunity cost. There's things you're not going to be able to do, because of that. So instead, you have Buddy. And, if there's a baby in it, it might be named Billy Budd. When a baby comes about, we don't look to it to give all the aspects of family context, etc. So here we can have effects that are ignored, consciously ignored. They can be re-examined. You list it so they can be easily re-examined. Exogenous effects. These are effects that are in the model, but the model doesn't calculate them. In other words, it takes them into account. Maybe it would be like declining marriage rate or something like that, or declining rate of fertility or something. You impose it on the model. You say, assume this. Assume this change over time. Or maybe it's a fixed constant. You just say, there is this birth rate for the model. But it's not dynamically evolving. It's not part of state. Endogenous is part of state. These are the things which change over time because the model calculates them. It's simulating a step-by-step evolution of where people live and whether they're in school or not, and their graduation and whether they find a job and all that sort of stuff. Those might be endogenous things. These are things whose dynamics are calculated as part of the model. So, exogenous things, they're in there. We're making assumptions about them, but they're fixed assumptions. The model's not updating them. We're not looking to calculate these things. Ignored things, we're abstracting them. We're not paying attention to gender. We're not paying attention to issues of, what someone's hair color is, or whether their height or weight, or say their height or what have you. So these things might be ignored altogether. Consciously ignored. And then, over time, these things may shift. You may choose in the next iteration of the model to put something that's exogenous into into endogenous. We shift something that way. Or you may find that, this is endogenous, but really it's not contributing in an obvious way to dynamics. Maybe we'll move it back up to exogenous. Or things that are ignored become exogenous. You start putting them in, seeing if they are likely to make a difference. Having this clear division is very helpful. Being clear in your mind about this division. Your model is not perfect. It's a thinking tool. Your mental model is not perfect. It'll take a long time to build a model close to perfection even for a problem. Do so in an intelligent way. It's like testing for, in some distant way, it's like testing for software development. You can't test everything in your software program. Universality dictates that, the only way we're going to test it is by running it. And we may never know, can only run it for so long. If it's a looping program, we can only run it for so long. We don't know if it's going to crash, the next minute. So we have to go after the intelligent thing. We have to go about it in a way that tries to be savvy, tries to get the greatest bang for the buck. And so it is with what we add to the models. So there's a notion of pattern-oriented modeling, which is very popular in agent-based modeling. And the idea here is that agent-based models occupy an arbitrarily rich model space, and because there's this risk of throwing things into the model, pattern-oriented modeling argued that, look, one of the most valuable things you can do when building models is to try to explain patterns. Okay? So you focus on the patterns, these observations, patterns to be explained. Sometimes they're called stylized facts. For example, in Michigan, they're quite up on that term. And these are quite similar to what system dynamics calls reference modes. These are quantitative time series patterns in system dynamics. So these would be patterns, of some function of time. Maybe it's something like that, but something we've observed. Maybe it's actually not quantitative patterns. Maybe it's something like, people's hemoglobin levels cycle. They go through a cycle. and we don't know how long it is. Or the business cycle. Maybe we have the business cycle. We know that you folks may not be aware of this, but there's long-term business cycles. So if you go back and look over the past century, you'll find that businesses go through periods of contraction and expansion. And if you look at the macroeconomy as a whole, there's a very pronounced business cycle. It goes, and I think it's time between cycles is something like 25 years. It goes up and down and up and down and up and down. And you might think, gosh, it's really weird because, business now is not like business before. Well, it turns out people have studied this with models. That's something to be explained, that sort of cycle. There you might be explaining the general presence of a cycle, or you might be explaining why there's this pattern of overshoot and collapse in reindeer population in Norway. That the number of reindeer go up and then they collapse down. Without trying to model an exact time series, we see that overshoot and collapse in a lot of animal species. So here we might have reference modes, quantitative or qualitative. And for agent-based models, you have additional things like patterns of heterogeneity, like how agents are spread out among different categories. Spatial patterns, like why do we see a certain type of prion concentrated near the lake shore, or what have you. Or maybe there's waves or clustering phenomena. And multi-scale phenomena that apply at multiple scales. So maybe we see, for example, crime data as different at sort of the individual level, patterns we see, or at the neighborhood level, or at the city level, or what have you. Phenomena that sort of play out over different scales. So in pattern-based modeling, we seek a model that will explain such patterns, tries to explain where these patterns come from. And the idea here is that patterns are pieces of information, which if the model didn't match, will cast suspicion of the model. It wouldn't seem on the face of it plausible, because people would say, no, wait a minute, you're not explaining this key thing. And typically the patterns that we choose are specific to the purpose. We choose a subset of patterns that are about things we care about. We try to rule out submodels using these patterns. So even if a given pattern is weak in constraining the model, for example, something like gonorrhea rates are higher among women than men, if you put a bunch of those patterns together, that's when you can really constrain sort of model structure, for example. And when we inspect model results, we may try to recognize other patterns which we haven't used in building the model, or predict them, and then we can actually go measure them. Okay, so these are some patterns that would be used in an agent-based model. Flocking behavior of sort of birds sort of coming together, and sort of you could see it if you've ever seen pigeons fly in a whole group of pigeons, or starlings in a field, or quelea in Africa. There's very sort of distinctive sort of patterns to these oscillations. I told you gradient patterns where things sort of change in some structured way, waves, cascaded transitions over time. Phase change phenomena. What do I mean by a phase change? Can anyone give me an example of a phase change with a physical substance? Water to ice, so that's good. With respect to disk drives, it turns out there's phase changes. In fact, your information that we store, the information that's being used to depict this, is based on, its success is based on phase changes. Phase changes associated with what? Magnetic domains. So basically, if you have magnetic particles, I'm not a physicist, but this is my understanding. If you have magnetic particles on the surface, they tend to align in one direction or another. And so if you want to store a bit, the way you can do it is by aligning them in a certain direction to indicate one, another direction, the opposite, to indicate zero. And if you heat up a disk drive enough, don't do this at home, but if you heat up a disk drive enough, the magnetic particles become disordered, and they don't point in any one direction, and it can't really store anything. But as you cool it down, sort of anneal it, they'll all cool down to a certain point, and they're all disordered, and then boom, they point one way. And which way they point, that's a matter of what we call symmetry breaking. Either points this way or points that way. And It's this very interesting point where they all suddenly break the symmetry, go one way. And they influence each other as to which way they go, and it's quite complex to figure out which way they can go. So that's an example of phase change that's perhaps less familiar to you. We actually see this though with health, for example. We see it with companies. We see it with projects, situations where there's just a dramatic change in things. Dramatic change for the worse, sometimes for the better in other cases. New York City, before and after Sandy. Folks remember Sandy? Big hurricane in New York City? So I have friends who are involved in modeling, fellow modeler, and I had 2 conference calls scheduled for the main day of Sandy with these colleagues. One was non-modeling, but they were applying some of our smartphone-based technologies. And I called up, no one answered, right? And they saw the most incredible things, like the power plant exploded in one case. It literally shattered. It blew up. They had to get relocated. There were fights in line for gases. One friend of mine was in their hotel. In their apartment. They looked down and there were a set of cars whose alarms had gone off. But the strange thing is the alarms had gone off because of flooding. So the cars were flooded to the level of their trunks, and the car alarm went off, so the front lights were going on and off under the water. Very strange phenomenon. In New York City's patterns totally changed before and after this, and it actually took weeks. So one of my friends was living in Queens for a week, in another borough of New York, outside of Manhattan. In other cases, it took weeks for my colleagues to get back. Totally different phenomenon, actually. And another phenomenon is cascading of failures. So this is one of the things which occurs in these emergencies. So if electricity goes down, communication channels go down. Communication channels goes down, gets in the way of transportation, right? Lights, traffic lights. You have that going down, transportation. It starts affecting the food distribution. Electricity also impacts water distribution. So cascading failures. Does this happen in computer systems? Cascading of failures? Or one thing fails, leads to another thing failing, to another thing failing? Turns out it does in big ways. One computer goes down in a web farm. The traffic that would have gone to there goes over to another system. Sometimes that can end up getting really, really slow and overloaded. People try to refresh, and it ends up they're putting in more traffic, and you can get this sort of cascading failures there as well. So we have a bunch of this is another one, punctuated equilibrium, where you occasionally see big change and then no change for a long time, big change. Those are patterns. Those are patterns to be explained just as much as time series. And it's arguably even more important for our understanding we'd be able to describe phenomenology like that. These patterns which are, we might not be able to predict exactly. Think about a phase change issue, or think about an issue with a spatial ring or something like that. We might not care exactly about reproducing some data about how wide it is, or the width of it, or the radius associated with it, or exactly what particle is pointed in what direction. But we want to capture this fact that the particles at a certain temperature all snap in the same direction, or that a city can totally change its sort of behavior. Fights can break out for distribution of gasoline in New York City, based on these conditions. These things are important, or that disease can be wiped out suddenly after persisting for centuries. Something like smallpox can go extinct. These are things which we often want to explain, and it's important to be able to have models that explain them. And some of the best models do not seek to exactly quantitatively predict at exactly what time this will occur, but they predict roughly what will happen. Climate models, in some cases, are like that. Okay, so let's talk about these things, and I'm going to finish up here in just 5 minutes. So let's talk about some components of this. We talked about purpose. Key operational elements for an agent-based model include things like entities, states, so these would be agents, for example, which could occur at different levels, states associated with the agent, parameters, and scale. So this might be sort of a multi-scale model: person, classroom, department, neighborhood, etc. Okay, so typically for an agent-based model, we're going to be deciding on, say, agents and their relationships. Maybe there's only one type of agent. Maybe there's several types. Maybe there's a worker in a car being produced, for example. Or maybe there's nurses, doctors, and patients in a hospital or what have you. Maybe there's deer, moose, and elk. Maybe caribou as well. Local environmental context. So here's some entities. Environment, sort of the local environment, spatial patches maybe, for example, a global environment, broader environment. And we might ask here, who interacts with who, sort of in what capacity? Do doctors and nurses interact, or does each, only interact with a patient? What are the states associated with them, and then what are the scales? We could use things like UML actually to talk about these relationships. This isn't done widely, but I think it's, ladies and gentlemen, if you are trained in computer science and agent-based modeling, your future is just wide open. Because there's too few people who know anything about UML, believe it or not, in agent-based modeling. There's a lot of physicists, a lot of people from background in economics or what have you, who don't have that sort of grounding. UML can be used to represent actors with certain roles, certain relationships, undertaking certain actions over time. Normally we do this to build up a system. So we ask about what are the functionality the system has to perform and who are the types of people interacting with it. But with a model, we might use that for the different actions the parties could undergo. We might have certain types of nesting relationships, these being cities, these being individuals in cities that we want to capture. Here, elements of what it considers state in ODD include things like parameters, mostly fixed characteristics. I don't like the use of the term as part of state, but that's how they use it. And then evolving components, aspects of state that evolve. So if you were to freeze your model, one useful way to think about the state of a model and ask you what it was, if there was some set of information, if you were to freeze your model, save it away, and you want to restart it later, what would you have to save away? What are the things that would have to be preserved for it to run going forward in the same way it would have originally run? That's your state. It's your state. And individuals in an agent-based model have state. In a system dynamics model, an aggregate model where we have stocks and flows, the state is entirely in the stocks. It's all in the stocks. So if you were to say it's the values away, and then you were to come back to it later, put those values in as your initial point, it'll go in exactly the same line going forward. So state characterizes the current situation of the system, the current status of the system. This distinction between parameters and states, I personally think is fairly important. Okay, I think I'm gonna skip over that. Scales. So there's a variety of scales you have to think about. Spatial scale. If you have space in your model, how broad is that? Is there sort of a discretization, or you have small units of space? Over time, what's your duration of simulation? And is there a step size in simulation? In both cases, often things are taken as kind of homogeneous within a step. What we'll see in any logic, this is worth remembering, is that by default time is continuous, and space can be either continuous or discrete. Okay? You can have step sizes, or you can just have it be continuous time. Things can happen as finely as desired. Okay? Then we have various aspects of local environment, which can be formalized as entities. Okay. For system dynamics, and I think I'll end here in just a bit, we have a variety of diagrammatic mechanisms that we use to diagram relationships between variables. And this is one of the most important. This will figure on your first problem set. Okay? We're going to talk about these in detail. And you'll find lectures by me online and YouTube where I go through this with you. But basically what we have here is a depiction on a semi-quantitative basis, or semi-qualitative, of certain variables and the relationship between those variables in terms of the polarity. Okay? And by filling in these lengths associated with polarity, we can come up with polarities for feedback loops. And if a feedback loop is associated with one polarity, say negative polarity, it's what's called balancing. So a change here will tend to ripple around and push back against that original change. So if we have a larger number of new infections, it lowers the number of susceptibles, which lowers the number of contacts with susceptibles, which lowers the number of new infections going forward from that. So it's almost as if we have a balancing phenomenon where, well, it increases, but then there's a pushback. And we'll see that there's negative feedbacks involved in a lot of variables. It's just like you're hungry, you get hungry, you go and you eat, and it decreases your hunger. That's an example of a balancing feedback. Homeostasis, the fact that our bodies are maintained at a certain fixed temperature with a certain fixed balance between salts and water. It's a function of these negative feedback loops. And our body is just lots and lots of these to regulate it. And you could think of all sorts of physiological ones. The other types of feedbacks are feedbacks associated with reinforcement. This is what's called a reinforcing loop. This is called a positive feedback loop. That's a negative feedback loop. Positive not in the sense that it's good, but in the sense that it's associated with a positive exponent, we think, associated with exponential. So it leads to a situation where you have a vicious cycle or virtuous cycle. A given change leads to a rippled through set of changes which ripple around, which cascade around, and amplify that original change. So here, number of new infections goes up. That increases the number of of infectives, which increases the number of contacts with infectives and increases yet further the number of new contacts with susceptibles, which increases yet further the number of new infections. So this is a unstable loop. It leads to very rapid growth associated with the number of new infections. The top one is a balancing loop. It balances out. It tends to pull back towards some steady state, towards some sort of situation of balance. It tends to balance out the system. Okay. This is a causal loop diagram. This is part and parcel of system dynamics, but you'll see it done after that. I think we'll sort of just abstract over a bunch of this stuff now, but suffice it to say, in agent-based modeling, you could create diagrams that are qualitative. This is in AnyLogic, and you can create diagrams that are quite evocative, that you understand well, but that are aren't yet fully quantitative. You can't run it because there's no transition likelihood specified and so on. It's just a diagram of how things proceed. And you could diagram things. This is another useful flow diagram, which can also, in fact, be drawn in AnyLogic, although this is not a depiction of one. This is a flow diagram associated with a certain process. Another diagram here. Here are several diagrams associated with a given person, several state charts associated with a person, which could be used to communicate basic structure without yet having defined them. Having defined the behaviors quantitatively, it gives an understanding of the types of behaviors that are possible and what is the next stage beyond what. And then we might have state. This here in AnyLogic showing aspects of state, variables, weight, age, cumulative cigarette smoke. And then there might be parameters that are more or less fixed assumptions, more or less, because sometimes they might change a little bit, but much less commonly. And being from computer science background, how many folks here have seen class diagrams? Yeah, okay, so everyone here. So you can use a class diagram. Here we have, in AnyLogic, we might diagram out, for example, a relationship between a bunch of classes. This could be agent classes like person, which lists the attributes which lists various methods supported by it, and main is another one. So these are useful high-level mappings, as it were, associated with our model. We're not yet at the point where this can be run, but we want to encode, we want to share with other people some understanding of what the elements of it will be. So we could add in a property there, etc. And these things, some of these are supported by any logic. This is, for example, a state diagram in any logic that can be used to sort of qualitatively describe things. So we're going to talk next time about model formulation a bit. I'll probably go over that quickly and highlight some things with model calibration and testing. And then we're going to go into system dynamics modeling in detail. We're going to revisit this issue of causal diagrams, and we're going to see elements of the feedback focus of system dynamics. Probably next time, if not the time beyond that. And just why we characterize these feedbacks, why they're so important to characterize. They're not arbitrary aspects of the system. They're important drivers for system behavior. They are often the keys for understanding internal system behavior and its response to disturbance from outside. Perturbation from outside is dictated often predominantly by the feedbacks. Okay, so that's all we're gonna get on today. I think I may release in the next day or two the first problem set, so keep your eye out for that. It will draw particularly on system dynamics components, okay?